In this video, we'll look at how the various logical concepts that we looked at in the first unit of the course apply to SD. So first of all, um, when we first started talking about SD, we gave a really rough account of what derivability is, but now we're in a position to give a precise definition. So a sentence is derivable in SD from a set of sentences gamma, if and only if there's a derivation in which all of the primary assumptions are members of gamma, and P occurs within the scope of only the primary assumptions. So auxiliary assumptions may have occurred in this derivation, but all of them have been discharged, and P is now only within the scope of the primary assumptions. And of course, we write this gamma single turnstile P. Um, One of the reasons why we say that all of the primary assumptions have to be members of gamma, but we don't say that all of the members of gamma have to be primary assumptions, is we want this definition to be applicable to infinite sets. And of course, you can't write, infinitely many primary assumptions at the start of a derivation. So in order to make sure that a sentence can be derivable from an infinite set of sentences, we just specify that there has to be some finite subset of that where if, that finite subset are all the primary assumptions of the derivation, then you can derive P from those. Um, and of course, then an argument is valid in SD if and only if the conclusion of the argument is derivable from the set of the premises. Now, there are a number of rules here that allow you to start off a derivation with an auxiliary assumption rather than starting it off with a set of primary assumptions, which is the usual way that we've been doing things. So, for example, let's say we just want to derive this, if A, then A. We can start the derivation off like this, right? Instead of starting it off with a primary assumption, we started off with this auxiliary assumption. We will assume A for purposes of conditional introduction. Then we just get A again on line 2 by reiteration. And then we infer if A, then A by, oh, it should say by conditional introduction there, but that appears to be missing. Um, Now, notice that there's no scope line to the left of if A, then A, right? There's a scope line up here marking off the scope of this assumption here, but there's no scope line down here because this is not actually within the scope of any assumptions. Um, what we've done is, we haven't derived it from any particular assumptions. The way that this is treated in SD is we've shown that the sentence can be derived from the empty set, right? The set that contains no sentences of SL. And if you can derive, so that's the empty set. If a sentence can be derived from the empty set, then we abbreviate it like this, just single turnstile P. And then the term is P is a theorem. So next we will define equivalence and inconsistency. So two sentences are equivalent in SD if and only if they're derivable from each other. If so, P and Q are equivalent if Q can be derived from the set containing only P, and P can be derived from the set containing only Q. And a set gamma is inconsistent in SD if and only if there's a sentence P such that gamma entails, or sorry, P is derivable from gamma, and the negation of P is also derivable from gamma. This might seem like an odd definition of inconsistency. One thing that you can say about it is this lines up with truth functional inconsistency. A set of sentences is inconsistent in SD if and only if it is truth functionally inconsistent. We talked about this in an earlier video, right? This is the soundness and completeness of SD, right? Gamma truth functionally entails P if and only if P is derivable in SD from gamma. That like immediately entails this, right? that an argument is going to be truth functionally valid if and only if that argument is valid in SD. It also has various other corollaries once you look at the definitions of these various concepts in for SL and then their definitions in SD. So, first of all, a sentence is truth functionally true if and only if it is a theorem. Sentence is truth functionally false if and only if its negation is a theorem. A sentence is truth functionally indeterminate if and only if it is not a theorem and its negation is not a theorem. Two sentences are truth functionally equivalent if and only if they're equivalent in SD. And a set is truth functionally inconsistent if and only if it's inconsistent in SD.